Morning.
Morning, sir.
Hello. Morning, sir.
Um, no, this is not a promise. This is a commitment. You'll get the problem sheets today. So,
Interesting. Thank you, sir. That would be very useful.
okay.
Sir, for reminder, sir.
Huh?
Should we remind you?
Come on. You did. I'm gonna put it together. I'm gonna have it for you for today.
So why not send it now just before class start? Or you want to wait till...
After class. After class. Okay. So this is what we're gonna do now. We're gonna go through some concepts for the magnetic field. And so we have this week and next week for lecture. And then the other week is your exam. So next week, I am going to do some problems which cover the concepts of what will be on the exam. It will not be your exam. Go through your exam and do exact problems, but it will cover concepts, right?
Sir, nothing wrong for change the values to clean, sir.
What?
Nothing is wrong if you just change the values, sir.
You're crazy, man. I mean, that means that you won't learn anything. You know, I get a WhatsApp message yesterday. Let me just read it to you, because I think it's so very important, and I wouldn't be doing my duty if I just go with this. It says, at the entrance of a gate of a university in South Africa, the following message was posted for contemplation. Destroying any nation does not require the use of atomic bombs or the use of long-range missiles. It only requires lowering the quality of education and allowing cheating in examination by the students. Patients die at the hands of such doctors. Buildings collapse at the hands of such engineers. Money is lost at the hands of such economists and accountants. Humanity dies at the hands of such religious scholars. Justice is lost at the hands of such judges. The collapse of education is the collapse of the nation. I mean, even if I said it myself, I couldn't say it better. I would be doing you injustice, give you questions, and just change the numbers of the examples that we do. You have to demonstrate that you study the material and understand it. Or I will be, Jamaica is collapsing already. I'll be contributing to further collapse. I will not do that. I sacrifice enough to be here to help. So forgive me if I won't do that. So don't ask me that again. What I will do.
No, sir, I did a little joke, sir. I did a little joke.
Me take it serious, man. Take it serious, plan. Hello. Hello. Yeah, I'm doing good. Yeah, man, I'm in class now. I'll call you after class. Yeah, I'll call you after class. Yeah, yeah. Right. Okay. Yeah. Back with you guys. So, okay. Let me take my register. All right. Remember, we looked at the electrostatic boundary condition. Right. Now we are going to look at the magnetic boundary condition. So the conditions of the magnetic field existing at the boundary of two media when a magnetic field passes from one medium to the other are called boundary conditions for the magnetic field, or simply magnetic boundary condition. When we consider magnetic boundary conditions, the conditions R, B, and H are studied at the boundary. Now, what is B and H? Similar to from the electrostatic condition. That's a question.
I can chip up.
Huh?
Repeat the question,
Yeah,
sir.
repeat the question, sir. I kind of go where the while ago.
Yeah, we are going to study B and H at the boundary. What's that similar to in electrostatic boundary condition?
Ah, the charger, the charge at the boundary, sir. The charge.
When we studied electrostatic boundary condition, what did we study?
Oh, the D and E, sir. Electric field and density.
D and E. So it's
Oh.
so we are going to run the this is supposed to be, that's why you can't let the thing pile up in them, because this is just supposed to be a follow-on from the D and E. So this is like D and E in electrostatics or electric field intensity. The boundary between the two different magnetic material is considered the study conditions of B and H at the boundary. Both the vectors are resolved into two components, just like in electrostatics. The tangential to the boundary and the normal to the boundary. So, here we are. Right? We're going to look at the normal boundary condition. So here you have your B field. You resolve it into a tangential component and a normal component. Right? So here you have your similar pillbox that we used earlier. So this is what we're gonna do. To find a normal component of B, select a closed Gaussian surface in the form of a circular cylinder as shown in the figure. So we select a Gaussian surface here. A cylinder, right? Let the height of the cylinder be delta H. Here's delta H. And be placed in such a way that half is above the surface and half is in one medium and half is in the other. Now this is what we're gonna do. According to Gauss's law for the magnetic field, the integral around the closed surface, B dot ds is 0. So B dot ds over the closed surface is 0. I'm gonna move up some to make a mental picture of what we have here. Because I want to move.
Repeat that, sir.
I said I'm going to move out of the picture. So you make a mental picture of what we have here. So we can move a little quickly. The surface integral must be evaluated over 3 surfaces: the top, the bottom, and the side. So the integral of B dot ds is the integral B dot ds for the top, B dot ds for the bottom, and B dot ds for going around the cylinder. We are interested in the condition at the boundary. So we're going to reduce, we'll have to go. We're going to reduce this delta H to the boundary. So we're going to squeeze this cylinder. All right? So the cylinder tends to boundary, and only top and bottom surface can contribute to the surface integral, because delta H go to 0. So the lateral part just disappear, right? The surface integral are calculated for top, bottom surfaces only. These surfaces are very small. Let the magnitude of the normal component of B be N1 and Bn2 in medium 1 and 2 respectively. As both the surfaces are very small, we can assume Bn1 and Bn2 constant over their surface. Hence we have for the top, B dot ds is B normal 1 the integral of the surface, which is delta S. And for the bottom, it's a similar thing. For lateral surfaces, B dot ds is 0. Why? Why is B dot ds 0?
So this has something to do with the B being normal to one of the things right there, or like parallel to one of the things.
No, B dot ds is 0.
So you make delta H equals 0.
Because we make delta H equals 0. We shrink it.
So when as delta H approaches 0, eventually the bottom, the lateral, the bottom surface integral and the top surface integral will be the same.
Exactly. Which is what we have. Which is what we have here. Right. B normal 1 delta S minus B normal 2 delta S is 0. And when you solve that now, you come to this. What was the parallel equation in electrostatics?
The parallel equation, sir?
In electrostatics.
So that's the one with E at normal, something like that. It was E in 1,
E-
E in 2.
Tell me.
E in 1 equal E in 2. Yeah, bound.
No, sir.
Sir, another permittivity times the electric field.
Is the boundary like the boundary condition where like equal to this, you mean, sir?
No.
The E equals E tan plus En.
In electrostatics,
Oh,
E tangential 1 is equal to E tangential 2. And D normal 1 equal D normal 2. Remember?
Say it again, sir.
In electrostatic, we have E tangential 1 equal E tangential 2. And D normal 1 equal D normal 2.
Oh, that it means, sir.
No. In magnetostatics, you have B normal 1, and I show you why. Equal B normal 2. So let's go search for what H is in the between the two medium. We know that B equal mu H. So mu H normal 1 equal mu 2 H normal 2. And if we divide this out, H normal 1 over H normal 2 equal mu 2 over mu 1, which is equal to this. Right? So the normal one, the normal two, which is this. So look at the tangential component now.
Sorry,
Okay, question.
with the normal component of H, did you make any mention of it being in the same plane? So like the same X, Y, if it's only if it's at the same height. I mean, because it's normal.
Yeah, but we remember we just use it, we just deal with B, you know. In other words. In other words. Yes, Sir Paduri. Yeah, man. I need to sign off on my exams, but I won't be coming in. So can you sign off on them for me?
Okay, I believe it's a face-to-face. When is that?
You just go to Mr. Daly.
No, when?
Yeah, you can go and sign off on it today.
Okay. Actually, I'm a bit far from Kingston. That's why I'm asking when.
Well, or Monday morning, early Monday morning.
Monday morning, we can go and do anything we want to. No problem.
Yeah, just go and sign off on them.
Okay. So, you will be not coming for the examination?
No.
All right. So, you want me to go there first half hour before the exam starts and look at the paper and then so it becomes that's all.
Yes.
So, but when is the exam?
I think it's the 22nd.
Okay. But Monday I need to go and
Yeah.
Maybe I'll call you on Monday.
Yeah, just sign off on them for me because
No problem, God.
yeah.
No problem. So how things?
I'm just trying to keep me behind safe, keep home.
Yeah, man, everything same issue, It's been like almost 1 year or 1.5 years we carry family outside,
Yeah.
Same situation. Only to the supermarket. And mostly usually I go and deal with it and come back. Remember, how young one.
Yeah. You have to be extra careful.
Extra careful. So the same thing that.
But you take your vaccines though.
Yes. But for the children, there is no vaccine. Because the first one is around 7 years old and the young one is 1. So no vaccine for them yet.
Right.
We both got the Astra.
Yes.
All right. So Monday morning, I go and sign it off, and as soon as we finish that, I will give you a call.
Okay, thanks.
No problem.
Okay. Who asked me a question again? This is B, This is B in region 1, and this is B in region 2. Right? So we just equate them and cross multiply, and we come to this. In other words, in electrostatic, you have D normal one equal D normal 2. Right? Which is this? Well, D would be equivalent to B in magnetostatics.
Oh,
But you see,
it would be like just the magnetic effect due to D. So
no. That's not what I'm saying. I'm just trying to draw a parallel between the two. Right? Ask the question again, let me see if I answer it wrong.
so I was asking where you have the H at the normal. I was saying since the both the objects were at the same normal, at the same height, because as I said, you reduce it to 0. So I was saying it's due to them being at a normal. What if there was it's one object, so
No, remember, we have a vector, we have a magnetic field, right? We have a magnetic field. Here's a magnetic field intensity, right? And we resolve it in the normal component and the tangential component. So we just use this pillbox to deal with the normal component, right? Then we're gonna move on to deal with the tangential component, but we are now, for the time being, we are only dealing with the normal component. You with me?
yeah, the normal, as I said, we have bar B in, so we don't want to be using that for the pillbox.
Come again?
In determining bar B equal mu bar H, the vector B equal mu vector H. As I said, it's a normal. So
Yeah,
we would want to be
right
using that magnetic effect.
Right now, we are only dealing with the normal component
All right.
to the surface because we resolve the entire magnetic field vector into two components, the normal and the tangential. So we are only treating the normal right now. So based on our analysis up here, we have already established that B normal 1 equal B normal 2. But B equal mu H. So mu normal 1 times mu 1 is equal mu normal 2 times mu 2, which is exactly this.
Yes.
So we just put the H on one side and the mu on the other side, and we get this. So if you look at this equation, right? No, look at this now. Go back here. If you look at this, you're going from one medium to the next. Whatever is happening going up to the boundary is the same thing happening going across the boundary, according to this, for B. So we can say that B is continuous at the boundary. But when we separate it out now, B mu H, and go through this, H normal 1 is not equal to H normal 2. So H is not continuous at the boundary. B is continuous at the boundary. H is not continuous at the boundary. When we look at the tangential component now, everything will just fall into place.
All right. Just at one level. So I'm just looking at it at because it is at one level, so it's equal, and that kind of explains it for me.
Okay. All right. So let us look at the tangential component now. Ampere's circuit law. H integral around the closed part of H that DL equal the current enclosed. So consider this closed part. All right. So we are going to go from A to B, B to C, C to D, and D back to A. That's your closed part. And your current is flowing on the surface here. So H dot DL equal I. H dot DL equal A to B, B to C. Oh, wait, what is now? Oh.
Yes, free, sir. What is that, sir?
What?
The little, it look like a 1 or a L or something. Oh, it's a 1, sir. It's a 1.
That's the one. H dot DL is A to B, B to 2, 2 to C, C to D, D to 1, 1 to A. Right? How much is supposed to have? 6.
Sir, could you
1, 2, 3, 4, 5, 6.
where you have those dots on the diagram? Could you just run through? Are the dots?
Where's that?
What? Where you have? It says the Gaussian surface. You have a dot
Yeah.
at the center, and then you have 1 and 2. Is that along that the semicircular part, or is it along the object?
We don't have
I'm pretty sure it's the intersection there.
Yeah, it's just the intersection.
Oh, so it has nothing to do with the actual height.
I
No.
mean, No?
Go ahead, go ahead.
Doesn't it imply the midpoint, sir, of the
Yeah,
shape?
it's the midpoint. It's the midpoint because remember we have half. So these dots are just illustration. Half of this, half of this. You'll see why. Okay, we didn't split up here. We split up this side, and you will see why. All right, just read that because you're gonna read faster than I can.
Hey, sir.
You have to tell me when I can move on.
Sir, like how you multiply h tangent 2 by the change in height divided by 2, why wouldn't we do the same for h tangent 1? Isn't it a case where tangent 1 and tangent 2 supposed to be?
No, man. One is the here's that one, you know. We didn't divide it up. We're shrinking this way. So this is tan one, this is tan two.
Oh, understand, sir.
Sir, medium one and medium two, sir. And
What about them?
sir, where at the medium two would be those objects, and medium one would be like the ground it is on, something like.
I mean, it don't have to be an object, you know. There are just any two things with different permeability.
Permittivity.
Permittivity.
To move on.
No, I was on the last part, so we kind of never really underlined that well.
Okay, let me go back up.
I think you can go on now, sir.
So h times the distance, the object, that size, is it like for vector, like voltage, electric potentials, where you have the work times dl or something?
Not quite if I understand that question.
Whereas I think you probably covered the equation in a previous class. We have kdw equals h tan 1 delta w plus the equation before this one. Where you have, when you multiply h times delta w, it's a component of the surface current. kdw. Yeah, k dot dw equals h tan 1 delta w.
Yeah. So K is the surface current. This is I, right? But it's a surface current, so is K. It's a surface current times the width. It's the same thing as this now, except that this, no, wait. It's ideal for for line, KdW for surface.
Like the current density and
Right. This is surface current density times the width. Give you the total current I.
but we have the H times the delta W. It's but H wouldn't be surface current.
No, but remember the Ampere circuit law. Remember at the beginning, man. You'll get it. Don't worry yourself. Mm-mm. This is it. H dot DL equal I enclosed. So we are saying that I is a surface current, K. So K is surface current multiplied by the width delta W, the current passing. So H dot DL equal K dW.
Oh, all right. So, and then it just take the over the entire.
Right. Anyway, here you have H tangential 1 equal H tangential 2. So for electrostatics, you have E tangential 1 equal E tangential 2, and B normal 1, and D normal 1 equal D normal 2. Magnetostatics, you have B normal 1 equal B normal 2, and H tangential 1 equal H tangential 2. So H is continuous at the surface, but B is not. And this vector stuff is exactly what we did in electrostatics.
It's you just change the direction of the force. The magnetic force is different from the electrostatic force.
All right. So we are going to pause there until 2 o'clock. We're going to do a little bit more. Then we do some examples.
Sir.
Yeah.
I'm not sure if it is too late now, but I think a lot of our class were hoping to get another word in regards to the exam.
Yeah, the exam is already decided. I can't change it again. It's face to face on the 22nd.
Okay.
Sir, time has a problem, sir.
Well, you have to take that up with the program director, you know. That's out of my hands. I'm sure if you call Mr. Daly, he will listen.
All right, sir.
So see you at 2.
So
Sir,
wait,
remember I'm gonna send
sir.
it up now, sir.
Yeah, man, we are going to get it today, guaranteed.
Yes, I'm gonna try to get it before 2, you know, sir. 'Cause after 2, you know, answer me again, no, sir.
No, man, you get it today. Don't worry yourself. You get it today, guaranteed. We will answer you. But you get it today.
Make sure you hold a promise, sir.
Aye. You're getting it today.